because we know the equation for this, don't we? It's AC over lambda. We can calculate the energy of the transition using this, and then we can relate it to what we can see in terms of wavelength using that equation. But they're in opposite signs to each other. This measures the electron, this measures the photon. So whatever is given off by the electron is essentially absorbed by the photon so that we can see it, or vice versa. Okay, so then let's look at how we're going to define this transition.
So the signs could be switched, correct?
No, not likely.
No, so it will always,
it will always be like that. Yeah.
Okay.
It will always be like that. So we're going to put this in the form of a final minus initial calculation. So we'll look at the final minus the initial. This equation applies to both of them. So instead of doing two of those things, you know, minus 2.1 times 10 minus 18 times that and subtract the other one, we just lump them together. So we put the two terms together, the final state minus the initial state, both of them squared, both of them being the n values. I should say this is the change. So if we know what these are, in terms of where the electron was and where it has gone, we can calculate the energy change in the electron. And whatever that change is equal to the opposite sign for the energy change in the photon, which we then can use to calculate the wavelength of that light. So let's do an example to illustrate that. This is similar to the calculation we'll be doing on Tuesday in our lab. We're going to look at the wavelength of light So we're going to calculate the wavelength of light emitted, and then we're going to also decide we'll come to this question second. Is this a visible transition? Or can we see it with our eyes? So in order to do this, we need to first calculate the energy change of the electron. So it's minus 2.18 times 10 to the minus 18th. And we're going to use the final minus the initial state. So what's the final? 5. So it's 1 over 5 squared, and the initial state is 1 over 6 squared. This is 1 over 25, and this is 1 over 36. It's 0.04. If you can do this all in one step in your calculator, you have my respect, because I can't. to 8. So that difference is what, 0.1012? All right. Yeah. That's a positive difference. Bless you.
What's the sign?
It's a this is bigger, so that's smaller, so that part is positive.
I know, but like, what, like, what are we measuring here?
Huh?
The wavelength. So is it meters?
Well, we're not calculating wavelength, we're just calculating this. And then we're gonna put that into this equation to calculate wavelength. We need the energy of the electron first before we can think about the light that's given off.
So that equation is strictly for the n equals 6 and...
Right. This is strictly for
Energy.
the energy of the electron when it moves from one spot to another. That's all. And then the second part of it is we equate the energy change of the electron to what we can either see or not see. And that's how we get the wavelength. So now we have I got 2.62 times 10 to the minus 20. Is that good? Okay.
Putting it in that equation?
So now we're going to take this and put it over there, but we're changing the sign. Because this is the energy change of the electron, we need to look at what we can see visibly. It has to be a positive number.
And they have to equal.
Yeah, it's the same number,
Okay.
it's just different sign. So now we're going to put it in the HC. We're going to put it into this equation to solve for this. To help us decide, is that a visible transition or is it something else? We're going to take this number, which is the negative of this, so positive number. And this is 6.626 times 10 to the minus 34. And this is 3 times 10 to the 8. And on the bottom we have wavelength.
How did you get the negative 2.62?
This number times 0.012. This is the difference in this term. This number, negative 8, I'm sorry, this number times this. Sorry, not that number. So I wonder what the exponent will be on this. Anybody have any idea?
Positive.
So what do we got? I got 7.59 times 10 to the minus 6. Yeah? So lambda is 7.59 times 10 to the minus 6. And the units are
Meters.
meters. So now we need to answer the question, is this a visible transition? How do we know? What can we see in the electromagnetic spectrum? We can see between red and violet. And red we said was about 750 nanometers, and violet is about 400 nanometers. So somehow we have to get this to nanometers to help us make this decision. Right?
You multiply 10 to the negative 1 to get nanometers.
So let's go back to the way that we, 7.59 times 10 to the minus 6 meters. And what's the conversion?
1 meter equals 10 to the 9 nanometers.
10 to the 9th nanometers up here, and 1 meter on the bottom. So again, if you always do it this way, you don't have to think about whether do I multiply or divide and what goes where. So that is what, 7,590? Nanometers.
Oh yeah, so probably not.
Probably not, huh?
Probably can't see that thing.
Because that's on the left-hand side of red. So it's infrared and going further to the left. So we can't see that transition.
Not like microwaves and stuff.
It probably not quite that far, but it's certainly trending in that direction. So again, keep in mind that roughly violet and red. Over here is ultraviolet, over here is infrared. And as we go further and further to the left, this number gets bigger. So this would tell us that we're, down in that area somewhere. Fairly low, fairly long wavelength, which means also fairly low
Frequency.
Okay. All right, good. Let's do another one of them. So let's look at what happens when we go from n equals 5 to n equals 2. We're going to use the same equation that we used here. And so that's negative 2.18 times 10 to the minus 6, 18. The other 6. And then what goes inside? Where's my final?
2.
Final is 1 over 2 squared, okay? And initial is 1 over 5 squared. So this is 0.25 minus 0.04, I think. And is that right? And that should be what, 0.21? 0.21 times that, and that will give us the energy of the electron. .58 times 10 to the minus 19. Joules, that's the energy change in the electron. And in order to make a decision on the wavelength, we need to convert the sign to positive, and then use the hc over lambda equation to find the wavelength. This expression is always true. So on Tuesday, when we do calculations exactly like this, not with the same numbers, but exactly this format, and you decide you're going to give me your report with a negative wavelength, I will not be happy. Right? Don't worry, we'll address that again on Tuesday. Okay, so we have 4.58 times 10 to the minus 19 And we need H, 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by the wavelength. And the wavelength then
So we changed the negative now?
yeah, so whatever the electron releases is equal to the opposite sign of what the photon is actually showing.
Which one of those is the speed of light?
This one,
C. And what is H? Again?
Planck's constant.
Planck.
It's always that number, and this is always that number.
Nice.
So the only things that change are that and that.
H is the constant.
I got 4.34 times 10 to the minus 7. Yeah. Meters. Visible or not visible?
Visible.
How do we know?
400.
Yeah. So this is how many nanometers? 434. All right. So it's 434 nanometers. We know that it's somewhere in here. So if we saw that transition in, through a prism, it should be the color violet, roughly, somewhere in that area. Probably blue, maybe closer to blue violet, but definitely with a violet component. So these are all done exactly the same way, regardless of whether I'm going from 6 to 5 or 5 to 2 or 7 to 4 or whatever. They're all done exactly the same way. And we never get negative wavelengths, just like we never get negative mass, right? Right. Okay, so that is that's really all there is in chapter 7. I do want to do one more example that I didn't do the other day. Let me see if I can think about. Oh, wait 1 second. We're going to go back to I'm going to do one more example of the photoelectric effect, because I want to do kind of a different calculation and stress a different point. So we have the following piece of information. So let's do that calculation. So when we see a question that speaks about ejecting electrons from the surface of a metal, we're speaking about the photoelectric effect. Where we spoke about shining a light or a light source on the surface of a metal and the electrons are released. That's what Einstein study to come up with the concept of photons. So, this is a bit different from what we have seen previously. When we see mole, what does that mean? Because this equation, this applies to one photon. We have apparently a mole of photons. So how are we going to get from mole to just one? What's a photon? It's a particle, right?
Does one photon equal?
We have to use Avogadro's number. That's the only relationship we have between one of something and a mole of something. So let's start with this number. So this is in terms of kilojoules per mole. In order for us to calculate this, we need energy of one photon in what units? What is the unit for energy in that equation?
Joules.
In joules. So we have two conversions to make. We need to go from here to joules, and we need to go from here to particles. So let's do both of those conversions. Let's work on this one first. So kilojoules to joules. 1,000 on top, right?
Yep.
Okay. Well, that goes away. And now we need to convert to one photon. So we have one mole on the top to get rid of this. And how many on the bottom? Avogadro's number. 6.022 times 10 to the 23rd.
Like atoms, protons, like I don't know, is it atoms, particles?
It
Like
doesn't matter. It's just particles.
Oh.
Whatever you're talking about. Here we happen to be talking about photons. Could be atoms, could be photons, could be electrons, could be ions, could be anything. As long as it's particles. Remember, it's a counting unit.
okay.
If you forget, think about a dozen donuts. Not eggs, because they're weird. Dozen donuts. Okay, so let's calculate that energy. And that will now be joules per one photon, which we need up here to calculate wavelength.
Oh God.
7.5.
Times what? 10 to the...
Negative 19.
Oh, what? Dang, there's that
27, 19,
I thought it was
7.27?
20.
7.54,
Oh. Put this in parentheses.
What did you get? Get his in.
Yeah, he's got it right. 7.54 times 10 to the minus 19. Yeah. Joules per photon.
Yes.
Is that right?
Oh
Okay.
God, what even is that? Like,
Why?
it doesn't even look right.
What doesn't look right?
The J/photon. Confuse me.
I'm hurt by that. It is good. That's good. So what did we say E was? E usually had an exponent of
Negative 18.
negative 19.
18?
19. 19. So we're in the right ballpark, right? So let's now put that over here to find the wavelength.
Okay.
6.626 times 10 to the minus 19, 34. 3 times 10 to the 8th on the top, and that on the bottom. And the winner is 2 something, I'm guessing. No?
2.6.
How much?
2.64.
2.64 times 10 to the 7, negative
Okay.
7, huh? Yeah. Meters. Okay. So if we wanted to cause this to occur, we need to use a certain wavelength of radiation. So what color light should I use?
None. Can't see radiation.
Well, this is electromagnetic radiation, so the visible spectrum falls into that. So what color should I use to make that happen?
Make it red, violet, ultraviolet.
So how many nanometers is this? 264.
Ah,
Where is that?
infrared. Right?
It's on the right side of violet.
Yeah, it's ultraviolet.
So probably ultraviolet, okay? So the answer is no color.
No color.
It was a trick question.
So,
What I wanted you to think about was, okay, where is this? So if you see the question, well, what color is that? You're thinking, well, it's not any color. It's in the ultraviolet area of the spectrum. So we'd have to shine ultraviolet light in order to cause that to occur. Did you get that? No? So one thing, in some of these calculators, they're all some of them are a bit unusual. I'll leave it at that. When you take this and divide it by this, it doesn't understand what you want it to do unless you put this in parentheses. At least that's what I've seen with some of these.
Alright,
Yeah. Yeah.
I have to multiply those two versions and divide.
And then divide in parentheses, yeah. Because I think what's happening is if you put this over here, it's thinking, oh, I'm going to divide this by this and then multiply by that. And then it gives you the wrong answer.
That's
Okay.
all you know?
Hmm?
That's all you know?
No, not yet. That's all I know about chapter 7.
Oh, you gonna fit some chapter 8 in here?
Huh?
You gonna fit some chapter 8 in here?
Yeah, we're just do a little bit of chapter 8. Can I erase this or?
Go on.
Huh? So, in chapter 7. Oh,
Stop
sorry.
right there.
Okay.
Just right there, I just need the box.
Okay.
Thank you.
So in chapter 7, the important things were we spoke about electromagnetic radiation, and we have three equations that we'll use. Remember the three that we have are this one, where this is frequency, and this one, which we have used for pretty much. These two explain the relationship between frequency and wavelength, and also between wavelength and energy. And then we also have this one, we also have that equation, which helps us understand the energy involved with the transition of electrons and also the wavelength for those transitions. Those are really the equations that come from chapter 7. The math in this chapter, in my opinion, is not generally complicated. You just have to be careful about the units. And then we also talked about the spectrum. So you want to know where the visible spectrum is between what numbers generally. And then we talked about the quantum numbers, the first three. And so now in chapter 8, I don't think has any calculations. I know you're sad about that. Chapter 8 has to do with periodic trends. So we're going to speak about the periodic table and some important trends that we can obtain by knowing some additional information about the positions of the electrons. Some other things that will be highlights in this chapter is we'll be doing electronic configurations.
That sounds familiar.
And as I said, periodic trends, and we'll introduce the fourth quantum number. So those are the things that we'll see in chapter 8. So prior to this, we talked about the periodic law, and way back, I think in chapter 3, we spoke about the periodic law, and that periodic law said that elements are arranged according to increasing atomic number. And there was one other important aspect of the periodic law. Does anybody remember what that would be?
Elements that are alike are in the same row?
Good, group. Yeah, good. Okay. So they're arranged according to atomic number, and they are and so when we use the term grouped by similar properties, that means the vertical row, or vertical columns, I should say. Anything in that same column, we would expect to behave in a similar fashion. All right. So this is all the this is the what about element properties. We know this to be true, or we know that to be true. That's the what. We haven't talked yet about why is that true. So chapter 8 has to do with why is a periodic law true, or why do those patterns exist? So what we're going to examine is electron configuration, which will help us explain why, and certain trends that will help us explain why. So that's pretty much the important things from chapter 8. So the first thing we're going to talk about is electron configuration. I'm just going to introduce it. So electron configuration gives us a description of the electrons in their orbitals. And it essentially spells out the position of the electrons in their orbitals in kind of a shorthand form. And the electron configuration has the following format. It has the main energy level, which is N. It has the orbital, which is the L, and then it has, in the upper right-hand corner, the number of electrons in that particular orbital. So I know this is a bit confusing. Let's look at hydrogen as an example. Hydrogen is in the first row. It has one electron. So if this is 1, what's this? 0, which we know is equal to S. And how many electrons does hydrogen have? 1. This would be the electron configuration for the element hydrogen.
That's easy.
Isn't this pretty easy?
So once again, the important thing here is we have to remember the association between this, between the number for L and what that letter is. So for L equals 0, that's an S. For L equals 1, that's a P. For L equals 2, that's a B. As we make larger and larger elements, this will expand considerably and start to include some of these other letters. So if we were to go to helium, how many electrons does helium have? 2. They're both in the first row, right? They're still in L equals 0 or S, and that will now tell me the number of electrons for helium. So we're going to stop there, and we're going to pick up with the next row and continue forward so we see the building pattern and how we begin to add these other rows to it, or other orbitals to it. And now that is all I know. Let me see if I have any other